Hello and welcome to Applying Compression Techniques to Deblurring with Team Deblur. My name is Rebecca Wilson. My partners were Youn and Mariano Hernandez Calva. Our TA advisor was Talha, Faiz. So, deblurring, why does it matter? Images, especially those captured by video cameras, are often degraded by different sources of blur. A more realistic blur, as seen in the top right image, is very different from a uniform blur applied by a blur kernel, as seen in the bottom two images. Deblurring images can be an important precursor for other computer vision tasks, like classification or object detection, which require clearer images. Since it is a precursor, however, deblurring models need to have fast inference times. Moreover, a lot of image capturing tasks are conducted in edge environments, like autonomous vehicles, where the available compute resources are limited. Current state-of-the-art models for deblurring need to be faster and smaller to be effective. One way to produce a faster and smaller model is to compress an already existing one using pruning and distillation, but these techniques are not well studied for deblurring models. For our project, we compared two state-of-the-art deblurring models, DeblurGAN v2 and MSSNet, on the GoPro dataset. Based on our initial results, we then selected and compressed the better performing model, MSSNet, to see if we could maintain its higher performance while beating the lower inference times of DeblurGAN v2.
So MSSNet uses residual convolutional blocks as a backbone of its architecture. It also has several subnetworks that operate at various scales, and the outputs of these subnetworks interact with each other via concatenation and addition operations. This allows for the model to account for uneven blurring caused by things like varying distances in the image. The blocks highlighted in red are intermediate outputs generated by the network for multiple scales, and these will be important during our compression process. To compress the model, we use a two-stage structured pruning into distillation approach. Pruning is tricky due to the downstream shape dependencies caused by the residual addition. So to address this, we only prune the intermediate convolution in each residual block. We identified the three blocks that have the lowest L2 norm across the out channels and pruned the lowest 15% of the remaining out channels in each selected layer. We then continued training for 5 epochs to fine-tune the model and repeated this process for a total of 400 iterations. In pruning, we set the weights to 0, but this is just a notional compression since the channel is still intact. This step leads to very little real-world performance improvements since the number of operations doesn't actually change, and we can't just naively remove these connections since there are downstream dependencies on these intermediate features. So to address these issues, we then apply a distillation process. Here, the raw prune network is a teacher model to transfer knowledge to a smaller student network. The result is a smaller student network that has learned to mimic the outputs of the much larger network. The student network here is a new model with the correct prune network shape and the intermediate convolutions, and the input and output dimensions of the entire block are also scaled by a constant factor to further compress the model. We then conduct a forward pass on both models, add the loss at each intermediate output layer from the previous slide, and apply the backward pass to just the student network.
Our two primary metrics for performance are PSNR, or the peak signal-to-noise ratio, which measures the signal power to noise power, and SSIM, or the structural similarity index matrix, which measures the perceived quality of an image. Here are the results from our pruning compared to the original sharp image. We start on the right of the graphs with all filters remaining and then prune down towards the left. The results were unexpected, as pruning generally maintains performance until a threshold, after which performance collapses. Instead, we saw a gradual decrease throughout the pruning. This may be because we were too aggressive and pruned too many filters during each iteration. We chose the state highlighted in red as our baseline for the teacher network, as it provided a good balance between performance and pruned filters. Here you can see our final results. We achieved a 2.3x reduction in inference latency with a 10% decrease in PSNR and 1% in SSIM from the original MSSNet. Our PSNR and SSIM were higher than DeblurGAN v2 with a 21% reduction in inference time, achieving both our goals of maintaining the performance of MSSNet and beating the inference times of DeblurGAN v2. We observed a significant drop in performance after pruning and then a smaller drop again after distillation, indicating pruning to be the main source of error. Here we can see a progressive degradation in image quality between the baseline, pruned, and distilled MSSNet models. Compression loss can be seen in the distilled model, especially around the faces of the man and the woman. Comparing DeblurGAN to our distilled model, overall visual quality is similar, but ours appears to perform better with objects in the foreground. We were able to achieve our goals of producing a compressed MSSNet with better inference times, but our methods focused on reducing width of the filters instead of the depth of the network. As MSSNet is a very deep network, we may have achieved better results if we'd also pruned layers. A major complication we ran into was a lack of library support for pruning and distillation techniques. We had to implement our own. Going back to pruning, we could have been less aggressive, pruning fewer channels per iteration, reducing the accuracy loss overall. Our results are very promising and lend themselves well to follow-on compression, like quantization. Here are our references.